Welcome to our lesson on gravitational fields, and just for reference, this is in fact lesson 4.3. Okay, so what is a gravitational field? It is really an invisible sphere of influence, right? Let's pretend that you're standing here, we've got a campfire, right? And all around it is heat, right? This person is feeling heat. It's under the influence of this campfire, and this person who's further away also feels the heat from here, but it feels a lot less, right? This person who is over here also is under the influence of that heat, but is somewhere in between, has less. Gravitational fields kind of work the same way, right? Except it is an attractive pulling force rather than a thermal energy transfer. Well, I guess it's really heating transfer from a thermal store. So one way I like to visualize it is kind of like this. You've got several objects with mass. The more massive the object, the more influence it has upon other things that will want to be sliding towards it. So if I were to put a little tiny ball, let's say here, it's under the influence of both of these, but it's going to slide down towards this one. Whereas if I put, let's say, the object here, it would slide down towards this one rather than this one, even though it's under the influence of both these objects. So the question is, what is a gravitational field? Well, it's how much influence an object with mass has. This object has mass, and this is kind of its area of influence, this bending of the fabric, if you will. And again, it's not a perfect analogy, but it is one that just kind of helps you to visualize kind of what's going on here with the field. The field is how much is this being bent towards this object with mass. So this is actually evidenced by the acceleration of that test mass towards this object, right? The further we are away, the less this is going to be pulled towards here than if it were right here. It has more influence here than here, more acceleration here than here. All right, and so what we're going to do is we're going to combine our two formulas for force of gravity. So force of gravity is equal to force of gravity. Not much there. What we're looking for here really is that this is the mass times acceleration is equal to g m1 m2 over r squared. Now we notice that I've identified the test mass in both of these cases, and that's really because those test masses are going to cancel out and thus leave us with this general formula. We note that this is in fact our acceleration, which we will measure in meters per second squared, but it is really using g, what we're talking about is our gravitational field strength. And essentially, the gravitational field strength is evidenced by that acceleration, assuming no other forces are acting upon it. So, gravitational field strength near the Earth should be 9.81 if the acceleration due to gravity is 9.81 meters per second squared. Well, let's calculate that out. G is equal to gm over r squared. And what we're going to do is use Newton's law, Newton's gravitational constant, mass of the Earth, radius of the Earth. And when you calculate that out, you do in fact get 9.81. Now, remember, this distance is dependent strictly on two things. First of all, this is the mass of object. the mass of the object bending that fabric, if you will, that's causing that change, which is the gravitational field, right? So it's the mass of the object here, not the mass of the thing that we're testing. And this is how far we are away from it, right? Still the inverse square relationship, but this is the distance away. Right, if we think about again this picture here, the further we are away, the less acceleration we're going to have, the less bending we have, right? But it also depends on the mass. More massive objects bend this more than less massive ones, right? This object is less massive than this one, so it's bending it less, right? And so it is that inverse square relationship which we got here. We note that on the surface we are sitting at 9.81 and moves here. Everything here, this would actually be inside the Earth and is not really relevant, but as we move away from the Earth, what you're seeing is a less and less influence by that gravitational field. A few fun facts. Now, you don't need to memorize these, and I know they're not on the formula sheet, but for the purpose of our example, we've been able to calculate masses and radiuses of several bodies within our solar system, and that would include things like Venus, Mars, Neptune, the Moon, and so on. Right? The masses in kilograms are shown here, and the radiuses are. Now, when you're solving problems, you will either be given the information, or you will be solving for the information, or it will be irrelevant. Again, you do not need to memorize these. I'm just putting this here as they are fun facts. So example number 1. What is the acceleration due to gravity on Mercury? Well, we have to remember that Mercury has a mass of 3.3 times 10 to the 23 kilograms and a radius of 2.44 times 10 to the 6 meters. Okay, and that was from the slide before. So G is equal to capital G m over r squared, and that m is the mass of Mercury, and the r is the radius of Mercury if we want to know the acceleration due to gravity near the surface of Mercury. All right, so you're plugging in the numbers. Please make sure that you are squaring that radius. It is an r squared. And you find that the acceleration due to gravity, or the gravitational field strength, more accurately, is 3.7 newtons per kilogram. Again, we more or less call this a gravitational field strength as opposed to an acceleration because we're just talking about that force to the center of mass, ignoring all other forces such as resistance, friction, crosswinds, things holding other things up, etc. Well, all objects, in fact, do have this gravitational field strength. It's just that smaller objects, such as this 50 kilogram sphere with a radius of 40 centimeters, is going to have a much smaller gravitational field strength on its surface than Mercury did. So again, G equals capital G m over r squared. We're using, again, the mass of the object and the radius of the object. And what you find is that the acceleration due to gravity on a 50 kilogram sphere, or shall I say the gravitational field strength on the sphere, is 2.1 times 10 to the negative 8 newtons per kilogram. Number 3 here. How far above the Earth would we need to be in order for us to have a gravitational field strength equal to the surface of Mercury? Now, this is an interesting idea here, but if we think about it, here we are on Earth, and here it's 9.81. The question is, how far do we need to go? So then instead of this being a gravitational field strength of 9.81, it's actually 3.70. So the mass of the Earth remains unchanged, but what we're doing is we're changing the distance from that center in order to find out how far away we need to be. So G is equal to dm over r squared, right? We isolate the r squared and square root, but instead of G being 9.81, we're finding the distance again from there at where it's 3.70. We find that we need to be r is 1.04 times 10 to the 7 meters. But remember, this is the distance from the center of the Earth. So we actually need to subtract the radius of the Earth to find out how far away we are from the Earth. And so it's actually 4.01 times 10 to the 6 meters. So there are different types of weights. And I know we've taken a look at the force due to gravity before, but a true weight is a gravitational force acting upon the object. But the apparent weight is simply a negative equivalent of the normal force acting on the object. When things are weightless, there's no normal force acting upon it. There's still a gravitational field strength. There's just no apparent weight. And that's what we call weightlessness. It's not forcelessness. It's not that gravity doesn't exist there. It's just that it is no longer, we're no longer feeling it because we don't have a force acting upon the other way. That apparent weight is that negative equivalent. So this is an OK Go video called Upside Down and Inside Out. And what they've done here is they've shot in zero gravity in a plane in the sky that this is falling down in free fall mode, which is actually causing some of these neat little things. Right, and so this is actual true weightlessness. Not that it's actually in this plane, it is falling. However, they're falling at the same rate as the plane, and so you got all sorts of neat little effects, and that's weightlessness. So if you want to watch the whole video, you're going to have to actually go look on it on YouTube. So we're going to take a look at example 4. What is the apparent weight of a 90 kilogram M in an elevator accelerating 1 meter per second upwards? Now, again, remember, when we're talking apparent weight, what we're really looking at for here is the normal force. And secondly, because we're not told otherwise, we assume that this elevator is on Earth or near the surface of the Earth. So the net force is going to be gravity and the normal force acting on the object. The weight that we feel is that normal force. So at net force, we know we're accelerating 1 meter per second up. The force due to gravity, the true weight, is 90 times negative 9.81 meters per second squared. And the normal force is what we're looking for here. And so what you get is 90 is equal to negative 882.9 newtons, or 972.9 newtons as your normal force. This would be your apparent weight. This person would feel heavier as the elevator is accelerating upwards. Not as it's moving upwards if it were going at a constant velocity, but actually accelerating upwards, right? So typically in an elevator, right, you get on here and it has to accelerate up to start moving, and you get that little jolt, and then once it's picked up speed, it's now moving at a constant velocity and will slow down. So you'll feel heavier just at that moment where it speeds upwards. So just a couple of quick little reminders. First of all, the mass in this equation is the mass generating the gravitational field. No other mass is needed, right? So this object here is generating this gravitational field. This one here is generating this field. This one here is generating this field. And the apparent weight is equivalent to the normal force. And again, G is equal to Gm over R squared. Hope that helps everybody. If you do have questions, please let me know.